and geometric sequences. It's going to take us a couple of days to work through this, but I want you to understand that what we're learning, even though it's going to look new, is very related to functions. So keep that in mind as you work. Now you should have a piece of paper ready to go for notes, and on each slide that I want you to take notes on, it will say in the upper left hand corner to take notes on the slide, so you don't have to write everything down that we do. You should probably put a title on your piece of paper though, which you can just copy the title from this slide right here. Okay, so we're going to start with arithmetic sequences. If you think of the word arithmetic, hopefully you think of arithmetic, and the first thing you learn when you learn arithmetic is adding. So arithmetic sequences are all about adding. Okay, so I want you to take notes here, write this down. The difference between consecutive terms has to be constant to be an arithmetic sequence, or the same. So when you go from one number to the next, to the next, to the next, you have to have a constant difference, or in other words, you have to be adding the same amount. The constant difference is also known as the common difference, and the letter we use for the common difference is D for difference. It's also the number that you're adding each time. So you can either think of it as the difference between two numbers in a row, or you can think of it as what you're adding each time to the previous number. Here's an example, or several examples. 2, 3, 4, 5, 6, 7 is a sequence that is arithmetic. 1, 1.5, 2, 2.5, 3 is arithmetic. 5, 11, 17, 23, 29 is also arithmetic, and 10, 7, 4, 1, -2. So I want you to pause the video, write these down, and figure out the common difference, or in other words, what number are you adding each time? Okay, so now we're going to go over this. Hopefully you paused the video and did the questions. Here are the answers. For the first sequence, the common difference is 1. We're adding 1. For the second sequence, the common difference is 0.5. We're adding 0.5. For the third sequence, we're adding 6, so the common difference is 6. And for the fourth one, a little bit tricky, the common difference is -3 because we are adding -3 or subtracting 3. So that's how an arithmetic sequence works. Okay, now we're going to decide if these are arithmetic or not. So you have to figure out if you're adding the same amount each time. Instead of trying to figure out what you're adding each time, you can find the difference between any two numbers. And you should do this for all of them to see if it's arithmetic. So -6 minus -10, any term minus the one before it. In this case, we get 4. -2 minus -6, we get 4. 0 minus -2, we get 2. 2 minus 0 is 2. And as we continue that pattern, you can now see that the common difference is not constant or the same. So this is not an arithmetic sequence. For the second example, 11 minus 5 is 6. 17 minus 11 is 6. And as I continue through all of these differences, they're constant. We have the same difference each time, so this is arithmetic with a common difference of 6. Okay, so deciding if a sequence is arithmetic is the first step in working through an arithmetic problem. Here's the rule for an arithmetic sequence. A sub n equals a sub 1 plus n minus 1 times d. This is a rule that is given to you on your reference sheet, so you do not have to memorize this. How does this work? Write this down. Here's the formula again, and we're going to talk about each of the pieces. A sub n is any term of the sequence, so a sub 4 is the fourth term, and you can continue that on for any term. You can also think of this as y equals or even f of x equals in terms of this being a function. A sub 1 is the first term of the sequence. D is the common difference, or what you're adding. And notice the matching ends. So if I'm looking in this example over here for the fourth term, then I would plug in 4 for n. Okay, write this example down as well. We're going to use the rule a sub n equals -10 plus 4n to find the first 5 terms. You are simply going to plug in the numbers 1 through 5 and get answers. So a sub 1 is negative 10 plus 4 times 1, and that's equal to negative 6. This is just like plugging in x to a function f of x, okay? So you're changing the n's to the number instead of changing x to the number. So now we have a sub 2. That's negative 10 plus 4 times 2, which is negative 2. A sub 3, negative 10 plus 4 times 3, which is 2. And here's your last two terms. When you plug in 4, you get 6, and when you plug in 5, you get 10. So you're just plugging in numbers to get the first 5 terms. Does this look familiar to you at all? Well, this is a linear function, so it's just like plugging in x to a linear function and getting an output. Part 2 of the example is using the same rule. Write the value of n for which a sub n is 34. So we're going to change a sub n to 34. So that looks like this. 34 equals negative 10 plus 4n. And then you just solve for n. Add 10 to both sides. So 44 is 4n. Divide by 4, and n is 11. So you can figure out where in the sequence 34 should fall. 34 should be the 11th term in the sequence if you continued the pattern. Here's another example. We're going to write a rule for the nth term of the sequence, 32, 47, 62, 77. Then we'll find a sub 12. There's a common difference, so you're adding 15 to each term, so d is 15. Here's the formula again. 32 gets plugged in for A1, 15 gets plugged in for D, and it looks like this. You can then distribute the 15 and then combine like terms so that a sub n is 17 plus 15n, which by the way can also be written as 15n plus 17, which would look more like a linear function if you prefer. There's your rule. Now use the rule to find a sub 12. Plug in 12, and you have an answer of 197. Finding the rule prevents you from having to use the pattern all the way up to the 12th term. And this is very helpful if you need to get to like the 50th term, then you don't have to keep adding 50 times. You can just use the rule. Okay, moving on to geometric sequences. This is a little bit different. So write this down. A geometric sequence has a ratio of a term to its previous term that is constant. Ratio meaning division. This means that you multiply by the same number to get from one term to the next. This number that you multiply by is called the common ratio. R is the letter we use for R for ratio. Here's an example. 2, 4, 8, 16. Another example, 4, negative 8, 16, negative 32. 3, 9, 27, 81, 243. And 20, 10, 5, 2.5 are all examples. So I want you to pause the video yet again, write these down, and figure out what you're multiplying by or what is the common ratio for each example. Okay, so let's go over these. For the first one, the common ratio is 2 because we're multiplying by 2. For the second one, the common ratio is negative 2 because we're multiplying everything by negative 2. For the third one, the common ratio is 3. And for the fourth one, another little bit of a tricky one, your rule is to divide by 2, which makes your common ratio 1/2. That should look familiar because this is very similar to what we did, or in fact, exactly the same as what we did with our exponential functions, okay? So you can divide each term by the previous term to find the multiplication factor. Here's what that looks like. In the example from the previous page, 4, negative 8, 16, negative 32. If I take negative 8 and divide it by the previous term, 4, I get negative 2. If I take 16 and divide by the previous term, I get negative 2. If I take negative 32 and divide by the previous term, I get negative 2. So we have a geometric sequence which has a ratio of negative 2. What about this one? This is a little bit different than the one from the previous page. Notice the negative signs. So in this case, sometimes we're multiplying by 3 and sometimes we're multiplying by negative 3. And here's what this looks like. If I divide any term by the previous, I would find the ratio. This is not a common ratio. Sometimes it's 3 and sometimes it's negative 3. So this is not a geometric sequence because it does not have a common ratio. The rule for a geometric sequence is a sub n equals a sub 1 times r to the n minus 1. This is a rule, again, that's on your reference sheet. Write this down and let's talk about the parts. The first two parts are exactly the same as the previous one. A sub n is any term of the sequence, which could be a sub 4 being the fourth term, and again you can think of this as y equals. A sub 1 is the first term of the sequence. R is the common ratio, so what you're multiplying by. And again, notice that the n's are the same, so if you're looking for the fourth term, you plug in 4. Here's what that looks like. Using the rule a sub n equals 2 times 2 to the n minus 1, find the first 5 terms. Again, you're just going to plug in each of the numbers. A sub 1, we plug in 1 for n and get an answer of 2. Calculator will probably come in handy here. For 2, we plug in 2 for n and get an answer of 4. For 3, we plug in 3 for n and get an answer of 8. Similarly, here's what 4 and 5 look like, answers of 16 and 32. Does this look familiar? This is your exponential function, the same function we were working on just a couple of classes ago. Now let's use the same rule to find the value of n for which a sub n is 8. So we're going to set the rule equal to 8. So 8 is equal to 2 times 2 to the n minus 1. This is a hard equation to solve. You actually don't know how to solve this type of equation, but we will be able to figure out n. We're going to divide by 2 on both sides. So we're getting rid of this first 2 right here by dividing by it. That gives us 4 equals 2 to the n minus 1. Now, we don't know how to solve this equation, but we do know that 4 is equal to 2 to the second power. So that means that n minus 1 has to equal 2. The exponent has to be 2 for that equation to be true. And so adding 1 on both sides tells us that n is equal to 3. And next, this is the last thing here, we're going to write a rule for the nth term of this sequence and find a sub 8. So we should be able to figure out that this is a geometric sequence, just like it's an exponential function, because it has a common ratio. Let's find the common ratio. Just pick a number and the number before it, so you can't start with 5, you have to start with one of the others, and divide it by the number before it. In this case, 2 divided by 5 is 0.4. So we have a common ratio of 2/5 or 0.4. You can use either of those. Now we find the equation. 5 will get plugged in for a sub 1, r will get plugged in for r, and so this is a sub n equals 5 times 0.4 to the power n minus 1. There is your equation. Now we're going to use this equation to find a sub 8. So we just have to plug in 8. Find the 8th term, plug in 8. So a sub 8 is 5 times 0.4 to the 8 minus 1. 8 minus 1 is 7. And when you type this into your calculator, you're going to get an answer of 0.008192. A very small number, but you can see from the pattern that the numbers are getting small very quickly, so we would expect our answer to be quite a small number. That's all for now. I hope this got you thinking a lot about numbers and sequences and how they all work. And the biggest thing, again, that I want you to remember here is that these are completely 100% related to linear functions and exponential functions. So if you understood linear and exponential functions, then it might take a couple days, but you will understand the relationship between those and sequences, and it will make a lot of sense. I will see you in class.